In the last lecture, we saw how to find our p-value. Our p-value represented the amount of evidence we had to go against our null hypothesis. How unlikely was it to have gotten the results we did if the null hypothesis is true? Now what we need to consider, though, is how much evidence we need. In statistics, we call that level of need alpha. Alpha represents how much evidence we need. And different scenarios, as we talked about, may require, or should require probably, a different amount of evidence to go against your null hypothesis. This is what is going to be our threshold that we'll use for specific tests. We denote alpha, the Greek symbol alpha. Right, so hence alpha, right? It's denoted as that Greek symbol. Let's go back to the example that we've been carrying along through hypothesis tests to see how we can use this. I'm going to add alpha as our things to make note of, alpha. And again, it's denoted as the Greek symbol alpha, which represents our threshold. I think it's hard to grasp what alpha really is if we don't have a concrete number to set it as. So for the time being, bear with me. I think it will make a lot more sense in the next couple of minutes or so. I'm going to set our threshold level to some arbitrary value to start. I'm going to set our threshold level to 5% or 0.05. So just stay with me on this part of this where we have some predetermined threshold level. Again, it's going to make sense a little bit later on. What we'll notice in this specific scenario, when I set alpha to 5%, this arbitrary threshold, right? Our alpha level is less than our p-value. Our p-value is 3.59% roughly. Our threshold, our alpha level is 5%. Our p-value is less than alpha. Let's think about what that represents. Suppose we had a different sample proportion. For instance, in our previous sample proportion, we saw a sample proportion of 0.518. We received 1,295 odd rolls out of 2,500. Let's suppose, for instance, for argument's sake, we got a second sample proportion where we received 1,350 odd numbers or odd rolls out of 2,500. So everything's the same, except we received more odd rolls. And in this case, our sample proportion comes out to be 0.54 or 54%. Comparing these two sample proportions now, which one do you think offers more evidence to go against your null hypothesis and to support your HA? It seems like the larger sample proportion, 0.54. This would give you more evidence to support HA and to go against your null, right? It's farther away from 50% or a proportion of 0.50, and we're trying to prove it is bigger than 50%. So this second sample proportion, 0.54, should give us more evidence to support our claim than 0.518. Now watch what happens when I graph that visually. If I was to graph 0.54, look at where that will fall on our distribution, 0.54. Our p-value should be all this shaded stuff to the right. Look at how much smaller our p-value is for 0.54 compared to 0.518. It's a much smaller p-value. Yet, we just said that 0.54 is going to do a better job at supporting HA and going against our null hypothesis. What we've learned from this is that a smaller p-value gives you more evidence. Not the other way around. A big p-value doesn't give you more evidence. The smaller your p-value is, the more evidence you have for HA and to go against HO. The same thing would be true down here for our test statistic. That test statistic that we create, if we shaded everything to the right, we have a smaller area. A small p-value gives you more evidence to support HA. The smaller p-value we have, the more evidence we have for HA. So our threshold kind of works inversely to what we may think. We want our p-value to be smaller than our threshold. The smaller p-value we have, the more evidence we have. So what we'll do is this. We'll compare our p-value versus alpha. This will be the comparison that we are going to use for all hypothesis tests. P-value versus alpha. P-value versus alpha. The smaller p-value we have, the more evidence we have for HA, and the more evidence we have against HO, our null. Let's go back to our notes to check out some things. When we compare p-value to alpha, if our p-value is less than or equal to alpha, it can be less than or equal to alpha, what this represents is we have enough evidence to reject our null hypothesis. And more importantly, we have enough evidence to support the alternative. That's what we're trying to do with it. We found enough evidence. We crossed our threshold. We have enough evidence to support our alternative. So when our p-value is less than or equal to alpha, this is what we can support. This is called a statistically significant event or a statistically significant result, something that's unlikely to occur by chance alone. Right? Our p-value was 3.59%, which is less than 5%. Getting the sample proportion we did was very unlikely to occur by chance alone if I actually gave you a fair dice. So based on this evidence, based on this likelihood, we have enough evidence to reject our null hypothesis and to support the alternative. We're not saying it's definitely false and the HA is definitely true. We're not saying that. We're just saying we have enough evidence to support HA and enough evidence to go against HO. So I'll just write a little support kind of as to really highlight that. So supporting. We're not saying true and false. We're just enough evidence to support and enough evidence to reject. The other scenario is this. When our p-value is greater than alpha. So I'll write p-value greater than alpha. The reverse. What we say is we fail to reject the null hypothesis. And more importantly, we don't have enough evidence to fully support the alternative. We say this weird, almost double negative in statistics. Fail to reject. We fail to reject the null hypothesis and cannot fully support the alternative. So failing to reject, it's not saying it's true. It's not saying it's false. We don't have enough evidence to say it's true. We don't have enough evidence to say it's false. We haven't really learned anything about it. We haven't made any definitive conclusion. That second part cannot fully support the alternative. We're not saying it's false. We're not saying it's true. We just don't have enough evidence to fully support it. Again, we haven't learned anything about that. So when your p-value is greater than alpha, you don't really learn anything about your parameter. It's important to note we are not supporting the null. We are not supporting the null in this case. We should not say we accept the null hypothesis. There's a few reasons why this is, and let's think about them. Going back to that visualization. In this problem, our p-value is 3.59%, and our alpha was 5%. So our p-value is less than alpha. What this is saying is we have enough evidence, since our p-value is less than alpha, we have enough evidence to reject our null hypothesis and to support the alternative that the likelihood of rolling an odd dice, an odd number, is greater than 50%. We're not saying it's definitely true. We're just saying we found enough evidence to support that claim. You find me guilty. Suppose, though, our alpha level was a different value. Let's suppose, for this argument's sake, suppose we set alpha to be 1%. P-value is now greater than alpha. So now our p-value is still 3.59%, but it's bigger than alpha. In this scenario, we say the phrase, we fail to reject the null hypothesis, and we cannot fully support the alternative. We fail to reject that it equals 50%, and we cannot fully support that it's greater than 50%. Our p-value is larger than alpha. And that should make some sense to us, right? We probably shouldn't support that it equals exactly 50%. How likely is it that the proportion is exactly 50%? One outcome out of an infinite amount of possibilities. Again, we see this again, that's 0%. There's essentially a 0% chance that it's exactly 50%. So we shouldn't support it necessarily. On top of that, our sample proportion in actuality was 0.518. It was bigger than 50%. So it's not like we should definitely say it equals 50%. It was bigger. It's still some evidence to support HA. But let's not get carried away and support that it equals 50% just because it didn't reach our threshold level. We had some evidence for HA, just not enough to throw me in jail. Just not enough to find the defendant guilty. These tests are not designed to support the null hypothesis. They're designed to have evidence to support or not enough evidence to support the HA. Even if we had a crazy big p-value, that doesn't necessarily support the HO. Watch this, right? Our more extreme values are in terms of greater than values because we're trying to support greater than. Imagine we got a new sample proportion. I'll call this p hat 3. And imagine in this case, we got 0 out of 2,500 rolls that were odd. No odd rolls. Well, our p hat in that case is 0%, or 0. If I was to graph that out visually, maybe I'd put it right here. And since our HA is greater than, we would look for all this area, all that shaded stuff, everything over there. That area, that p-value, would be roughly, approximately 100%. Should we support that the proportion of throwing an odd number is 50% when we received 0 odd rolls out of 2,500 attempts? No, that's probably insane for us to support that it's 50-50. Yet we have a p-value of 100. Just because you have a big p-value does not mean you should support HO. We just saw 2 scenarios, kind of 3 scenarios, where none of these situations, a p-value greater than alpha, should support HO intuitively. Nor does it. So our conclusions, based on the amount of evidence we have, should always be in terms of HA. Do we support HA? Do we have enough evidence to support it? Or do we not have enough evidence to support it? Going back to our original problem with our original metrics now that we did all this, we had a p-value of 3.59% and an alpha value of 5%. Let's now focus on thinking about our alpha a little bit differently. Yes, it represents our threshold, but in our next lecture video, we're going to think about what alpha also represents. And now that 5% may make a little bit more sense to us.